Hello and welcome to Into the Abyss podcast. My name is Todd Decker and I'm here with Jacob. Jacob, welcome on.
Hi, thanks.
All right, so today we're going to talk about some mathematics and specifically category theory. Jacob's kind of my professional reference to anything mathematical, which I am very interested in, and he's a good person that I bounce questions off of and for as a free resource, so it's always very nice. And I've wanted to have you on for a while to come and talk about some of this stuff because I find it very interesting. And you are a mathematician, so it's perfect. So if you want, I could give kind of my own overview of it, and then you can comment on it. Just based on the stuff I've read. How's that sound?
Yeah, I think you had mentioned earlier some points about the transition of mathematics from a theory of, or from a kind of methods for solving equations to the study of the structures in which it is maybe possible to solve equations, or just the study of abstract structures in general. And I think that's a good kind of background framework to be thinking about category theory with.
Excellent. Yeah. Let's start there. So when we have our kind of online conversations and we talk about all sorts of stuff, but in our mathematics conversation, I had asked you a while back, what are some books that you really like? You know, I'm kind of interested in reading some stuff on mathematics because I'm always reading. And one of them was a book of abstract algebra by was it Charles Pinter?
That's right.
And in the introduction to that book, he kind of talks about the way mathematics developed historically, and that there was a critical point at which mathematicians started realizing mathematics can be more than just about solving specific problems or equations, but also abstracting a level back onto the nature of those problem solving itself. And in another book that you'd recommended was how to make pi, I think it was, by what's her name?
Eugenia Chang.
Eugenia Chang, thank you.
Okay.
And she had a very vivid analogy. Actually, this wasn't an analogy. This was just kind of a ladder of abstraction that she was talking about, where as people go through their education and learning about mathematics, they keep on moving in more and more levels of abstraction, and people kind of drop off along the way as it gets more abstract. But I guess starting from, just concrete objects, so kids sees there are objects, and then that you can have one object and two objects, and then so say it's object is an abstraction already, so let's just say it's a toy. So you have one ball and two balls, three balls. Oh, well, then you can abstract from that you can have one, two, or three of anything. And then so that's one level, and you get the idea of numbers, and then you can do operations like addition, subtraction, multiplication, and such. And then you can have equations where you take out specific numbers and just put in variables, and so on and so forth. So it keeps on getting more and more general, and in her ladder of abstraction, category theory was on the very far end of that. And as a historical example, the one I always think of is like Girdles and Completeness theorems, where it's more like about the nature of the nature of systems that can be constructed and what they're like, and rather than solving any specific problem. But and there are lots of examples of that in the history of mathematics. There's a one of my favorite SMBC comics. It shows this guy bursting into a room of mathematicians, and he's saying, "Good news, everyone! That equation or that problem we've been working on our whole lives turns out it can't be solved," and everyone's cheering. And then the caption says, "Mathematicians are weird." But I get it, because it's like there are certain problems that maybe you can't solve, but you can demonstrate that they can't be solved, and that's a different type of problem. But yeah, so I find that very interesting. So that was one reason of getting into that.
Yeah, I think so. This kind of habit of taking some problem to be solved and then extracting the structure from it that lets us solve the problem is really something that mathematics has just really kind of run with in the last, I guess, century and a half. So originally, mathematicians were very much kind of focused on solving individual problems, on taking a cubic polynomial and finding the roots of that polynomial. And then I think you alluded to this in the context of just the abstract algebra book, showing it was eventually shown that it's impossible to come up with a general form solution in terms of square roots and cube roots and et cetera of a degree 5 polynomial. So one that's like x to the 5th plus something x to the 4th plus et cetera, which was kind of a paradigm shift for mathematics. So one of the first instances of showing that there's a problem and it can't be solved, at least not with the tools that we wanted to solve it with. And so this kind of precipitated that shift towards focusing on structure rather than solely on just finding clever solutions to problems. And learning and understanding the structure has really been extremely useful in solving problems. Sometimes the analogy is given. This comes from Alexander Grothendieck, who is a very kind of celebrated French mathematician of the 20th century. He died a couple years back, and before his death, he had retired from mathematics because he was disillusioned with how everything had become kind of focused on, with how academia was kind of complicit in the the military order and all sorts of things. So he just kind of retired to a village in France and lived as a hermit, grew his own vegetables, and anyway, so he did that for about 20 years and refused really to do any math, or at least to tell anyone about the math he was doing. But his analogy was, there's kind of two approaches to solving a problem, and one is you think of this as like a nut to be opened, and so one approach is to kind of like take a chisel and a hammer. Maybe this is how French people open nuts. I don't know, but you like kind of like tap at it at like very specific points and until finally it just splits open, right? And contrasting that with kind of his approach, which is to kind of see this as you soak the nut in water for a few days or whatever until the skin or the shell just becomes soft and it just peels off, like I think he says like the skin of a ripe avocado. Or of kind of like the image, and sometimes you can just kind of refer to this in the context of mathematicians. You say the rising sea, and so it's like as the sea rises, it just kind of comes over the whatever hills and valleys there are, and just kind of fills it all in, and overwhelms whatever it is without really this direct effort of kind of to specifically pick at the things that are in the problem. Grothendieck is famous for kind of being behind some of these vast, sprawling reaches of very abstract theory. And the reason that kind of mathematicians celebrate him is because, well, there's a lot of stuff there. And then also it ended up being very useful for solving a lot of problems that they were interested in. And so this is kind of I guess the reason that mathematicians really got into abstract theory is that it can dissolve problems in the sense that you don't have to necessarily try. You can just you build the theory up enough, and kind of by a sequence of essentially trivial results, you end up with something very, very non-trivial that otherwise would have been impossible to expect or comprehend. Yeah.
I mean, I guess even as a general idea, beyond even just mathematics, the idea that you can demonstrate that a certain question can't be answered and demonstrate that conclusively is still a very interesting thing to learn.
Yeah, absolutely. And it's interesting how in different fields of math, there might be different reactions to that. So someone might prove, I've shown that this problem is NP complete. And to one group of mathematicians, they'll be like, woohoo, that means that it's computable. And the other one says, oh no, that means that it's basically impossible. And depending on what you're trying to do, both of those reactions could be appropriate. But it's still an important thing to know either way.
Yeah. Very nice. Cool. Should I give my own understanding of category theory?
Yeah.
Okay. So this is just basically I've had like three major sources for category theory. So one was the How to Make Pi, Wikipedia, and Stanford Encyclopedia of Philosophy. So I actually like the Wikipedia article was fairly easy to read. But I'll
take a quick look and see what's on there.
Yeah. Well, just kind of introducing me to some of the terminology, and I guess, and this is kind of nice because as a non-mathematician, I can kind of give it from that side. But a lot of the times, what I find in getting into a concept, it's kind of hard to know, like, okay, where do you dive in? Because there's like all of these terms and things that you may not know, and then you like try to go back and learn those terms, and then that leads to more terms, and a lot of times I find it's just like, don't worry about it. I'll just take it as just set that in your toolbox and say, okay, that means something. And,
observe the structure and not necessarily the definitions.
Very nice. Yes. Well, yeah. So one of the things, my first introduction when you brought this up was about the structure-based approach that is looking at the way things are put together rather than the constituent parts. So category theory, I guess one of the things that comes to mind immediately is that there are these diagrams.
Maybe I should draw a picture here.
Yeah.
That might be helpful. Right. So as you're saying, in a category, you think you have of this as having maybe a collection of objects. I'm going to call objects, maybe I'll call this X, and then I'll call this object Y. And as far as the category is concerned, these are just kind of like indivisible things. There's no structure to them individually. X could be anything, and the category doesn't care what it is. And then, as you're talking about, there are these other things that we typically, draw in diagrams like this. So they're called morphisms, or arrows, or different things like that. And again, each arrow doesn't, from the category's point of view, doesn't really have any sort of structure. It's just a thing that happens to be there, and it goes from one object to another object. And so the name morphism is probably, if you know Greek, it's not necessarily the best term for what this is. It's kind of evolved in mathematical usage. I think it started with isomorphism, which makes sense. It's kind of supposed to be a way in which two things can have the same form. And then that evolved into homomorphism. And then the category theorists were just like, and we'll chop off the first part and just call all of these things morphisms. That seems like a good idea. But then it just says, well, it's a form in Greek, or a formism. And so etymologically, it's kind of weird. So maybe, and then the key thing about morphisms, right, is if I have another object over here, call that Z, and I have another morphism here, then I can kind of glue them together. I can compose them and get another morphism from X to Z. So maybe if this one is called, this is one of the annoying things about category theory. So if I call this first morphism G and the second one F, then the morphism from X to G is F composed with G.
Right. And usually represented with, so objects, is that general to represent objects with the uppercase letters and then morphisms with lowercase?
Yes and no.
All right. That's usually how I see it, but.
Yeah, so you'll often use kind of letters starting with F, G, H, I, J for morphisms. Typically lowercase, and then sometimes people will use uppercase, sometimes people will use lowercase for objects.
Okay.
There are all sorts of conventions.
Right.
But yeah.
And as I recall, so the you said F composed G was the way you phrased the lower one there?
There are a number of ways that you could say that. So, I mean, you've probably seen that notation in maybe calculus or something. Mm-hmm. And so I remember when I was, in high school learning these things, I would read that, F of G, which is...
That's how I would normally,
fine.
Yeah.
And that's fine. The circle kind of looks like an O for of. Mm-hmm. Sometimes people will say F after G. That's helpful when you kind of look at, I have F and then G in the way that I write this here. Mm-hmm. But then I have G is the first thing that I do, and then F is the second thing that I do. So there's this kind of reversal. And that's why sometimes people will say F after G to remind you that kind of if I were drawing this diagram, F would be the one that comes after.
Mm-hmm. And so that's basically, is it correct to say that's a demonstration of the relation is... you could go from X to Y through G and then Y to Z through F, or you could just go straight from X to Z through the F on G.
Yeah. And the point is that those would be the same thing.
Right.
Right. So maybe if we think of this as, think of these things as like three cities, and, your morphisms are routes that you mm-hmm. could take from one city to another. Well, if I take a route from city X to city Y, and then another route from city Y to city Z, that just defines a route from city X to city Z.
Right. Okay. Yeah, and one of the things I find interesting as well that I've read is that you can also have these arrows that, the identity arrows that just go right back to an object, right? So which I guess is critical to the idea that you're defining these things by their structure, by their relations. Even an object itself, you don't just pay attention to the object, but the relation that it has to itself.
And yeah, in fact, kind of from a strictly formal perspective, if you have the identity morphisms, you don't need the objects. You just need to know what morphisms are in the category. Mm. No one ever thinks of it that way, but technically you could get by without the objects.
Interesting. Okay. Very interesting. Okay, so we have the objects and morphisms, and then as my understanding was, the objects and morphisms basically are the category, the combination of all that together, right?
And that's all there is to the category.
Okay, and that's it. Yeah, and then you can basically take that up a level, and so you have categories, and then kind of put in the place of the objects the categories, and do the same thing again. So then you have the arrows between the categories and have this same structure, and then the the morphisms in that case would be called functors. Is that right?
Yeah. So maybe let me call this category, say things in here like in category curly C, and I'm very bad at drawing curly letters, so this D might not be great, but so maybe so the idea is, yeah, we might have what we call actually I'm not going to write it like that. Right, so we might have a functor which we'll write capital F, and so what a functor does, right, is it kind of takes a picture of one category and kind of squeezes or transforms it into a picture in a different category. So that means that I get some object f of x, f of y, f of z, and I need to have all of these arrows that I had in the original category. And then this would be here f of g and f of f, and then I'd have kind of f of f after g, and that has to be equal to f of f after f of g. So that's what makes it a functor, is that I can it preserves kind of the way that things compose in the category.
In the way that morphisms did with objects.
Exactly.
Okay.
So it kind of gives me a picture of each object in my new category and a picture of each morphism, and that has to be kind of consistent with the way that it worked in the old category.
Right. Okay, great. And then, and then just to go over all the terminology, I understand you can do this again. Mm-hmm. So would these, this whole structure here, then D, would this be considered a new category?
Yeah. So you would typically start with some category and then another category. So you'd have those as given, mm-hmm. and then you would construct F as the functor from C to D. So by choosing an object of D corresponding to each object of C, and mm-hmm. then a morphism in D corresponding to each morphism in C.
Okay. All right. And then I understand the next level up, basically you would have a natural transformation. So would that be the same type of thing where you're taking this whole category and then instead of calling what was before morphisms or functors, you have natural transformations as the arrows?
Yeah, natural transformations are a little bit complicated to define. I'm not sure if it's worth trying to draw the whole diagram here right now, but yeah.
No, fair enough.
So the idea is, you have maybe a collection of categories. If you say, I'll have my objects be categories, and then my morphisms be functors. Mm-hmm. Turns out that I have a category of categories.
Right.
So things get meta. And then mm-hmm. if I look at the functors between any two categories, that also turns out to be a category. So it's a functor category. Okay. And the morphisms in that category are natural transformations between functors.
Excellent. Okay, great. And then my understanding is, that's sort of where the terminology stops, but you could, in principle, keep going, right?
Yes. And there's this whole field of kind of higher dimensional category theory, higher category mm-hmm. theory, that even most category theorists kind of throw up their hands and be like, I don't know what any of you are doing.
Yeah.
So it has a lot of very fascinating kind of ideas in it that turn out to be pretty useful in algebraic topology in particular. But again, it's a whole new level of abstraction. The thing that people want to work with are infinity categories, where you not only have kind of objects and morphisms between morphisms, and morphisms between morphisms between and
yeah. Well, so an analogy I think of is differentiation. Mm-hmm. So if you have a function and you can take a derivative of it, there are certain functions where, like, say e to the x, where it's just gonna, you can just keep differentiating and you're just gonna get back the same thing. Whereas if you have like a polynomial function, eventually you're just gonna get to one, right? I mean, you can only differentiate it a certain number of times, and then in manifolds. So I think of manifolds basically kind of like an abstract surface. Some can be differentiated infinitely. You could keep on going forever, and then some where you're eventually going to reach a point where you can't differentiate it anymore. Now, are there objects, or are there categories where like you reach a limit where there's just no more that you can get out of it, or can you in principle can you go on forever with anything?
Sure. So maybe there's a sense in which you can go on forever, and a sense in which there's no reason to do that.
Yeah.
So maybe let me give maybe some just very simple examples of categories, because you can the structure of a category is simple enough that you can just kind of like write down a category with a finite number of objects and just specify all of the morphisms and everything.
That'd be great. Yeah.
So maybe we could have a category that just has two objects. I'll call them X and Y. And okay, it has to have these identity morphisms. So I'll call this id X, and I'll call this id Y. And then I'll just say that it has one other morphism. I'll call that F, right?
Okay.
And this is a complete description of the category. Well, I need to say what are the compositions of these things. But the identities are supposed to kind of do nothing when I compose.
Okay.
So I should say that, I guess, F composed with id X must be equal to F, and then id Y composed with F should be equal also to F.
Mm-hmm.
And that's all you need to say, that's all the data that's associated with the category. There's nothing else.
Mm-hmm.
And so you could kind of look at this as, this is not the simplest possible category. The simplest possible category maybe would just have one object and just the identity morphism.
Yeah.
And if you looked at, okay, I could make this into a category, and the set of morphisms between X and Y, I could call that a category. Mm-hmm. But it would be a category with one object and one morphism. And I could keep going up in dimension, and all I would get at every point would just be this one object and one morphism.
Oh, okay. Yeah.
So it's just like you could keep infinitely differentiating a polynomial. At some point, you're just going to get zero every time.
Yeah. Okay. Yeah.
Whereas maybe here's another sort of category that's maybe more interesting, that has maybe infinitely categorical structure. So I'm going to think of, I have maybe like a surface, so a cylinder or a sphere or something, and I want to look at paths in that surface. So the objects of my category will be points on my surface, and the morphisms will just be paths. Mm-hmm. Okay, so those might be two morphisms in my category. There's infinitely many of them.
Okay.
But now I can say, all right, if I have a way of kind of scooting one path down to align with the other one, so in topology, that's called a homotopy. Mm-hmm. So this would be kind of like, okay, I'm just going to send this path down like this to line up with the other one. Okay, so that, you could think of that as a morphism between these two paths. So it's a you'd call that a two-morphism maybe. Mm-hmm. And well, if you think about it really hard and maybe write down some equations, you can think, oh, I could also think about homotopies between homotopies, of ways of kind of associating two of these things to each other. And it turns out that in general, you can go up arbitrarily high, and you will get you can get interesting information depending on what surface you're working with. Mm-hmm. So this is one of the principal examples of an interesting infinity category.
Okay, yeah, you're right. And then and it sounds like that would get difficult to conceptualize as you keep going up, right? Like, so you basically said
Yeah.
at a certain level, most people are basically, okay, I don't know what's going on here, right? I don't know
Yeah.
what you're doing.
And so the hard part about infinity category theory has been kind of building the tools to keep track of all of the moving parts, so that you don't have to do that by hand.
Yeah, that's what I was wondering. Is there a way to basically make this all into an algorithm that a computer can just handle, or is it does it require a level of mathematical intuition that hasn't been put into a program yet?
Um, that's a good and probably open question.
Uh-huh.
I think there are probably going to be problems that turn out to be undecidable in kind of formal computability sense.
Hmm.
But yeah, some of these things can be encoded. Part of it is just coming up with even like a human readable description that is not too long, that you can kind of get your hands on and work with, and that gives a nice way of representing all of the information you need to say, because there's rules about how composition has to work in a category, and then there's rules about how composition of two morphisms has to work in a two category, and so on and so forth. And these get progressively more and more complicated as you go up in dimension.
Mm-hmm.
And so the idea is, well, let's just, instead of doing that, let's define an infinity category in terms of some other stuff, and and kind of come up with a structure that lets us sweep that complexity under the rug.
Yeah. Okay. Nice. So, one of the things I find kind of interesting is the way that this has been proposed as an alternative foundation to mathematics. Alternative being to set theory, basically.
Mm-hmm.
So, how is that? I guess are there camps or teams within mathematics, and like how does that break down? Like, is there a team set theory versus a team set category theory for the foundations?
So yeah, I'm not super familiar with kind of the debates about foundations that go on. I see maybe there's a couple of points of not really contention even. I think among mathematicians that are interested in foundations, you have the group that just kind of work with different set theoretic things, trying to understand axioms and models of structures. And then there's there are groups of people working in things like homotopy type theory, which it turns out to be fairly categorical, and also amenable to doing things like automated proving. So helping computers either check or produce proofs of theorems on their own.
Yeah.
And that so that has more of a categorical feel, and it works differently than some of the standard foundations for math. But yeah, I'm not really up to date on kind of the.
Yeah. Well, that's fine. I was thinking maybe I should back up a second and kind of explain like why those would be different, and then you can fill in the details. So how we were talking about with the category, it's basically just you could just have the morphisms, just have the arrows without the objects. Whereas with set theory, the objects or elements are pretty important, right? So basically, you have a set, which would just be you have a certain number of elements in a set. You're collecting objects together and saying, okay, this is a set. So it seems like a fundamentally different approach, where objects are basically indispensable. You have to have them. They're what compose a set, versus an approach in category theory where you can basically dispense with them. You're looking at the relations, the morphisms between them.
Yeah, and I think a lot of category theorists have kind of felt like set theory gets in the way or is not the right kind of not the right kind of foundations to work with the things they were interested in. On the other hand, a lot of work in category theory is just kind of implicitly based in set theory.
Yes,
so,
that's the criticism I've been reading, is that you can't really have category theory as a foundation because it requires set theory within it.
Yeah. So, for instance, there are these notions of, I guess, a small category and a large category. So when we talked about maybe a category of categories, we were brushing over this notion of size, because in some sense, some collections of things are too big to be sets. So you might think, well, I can't have a set of all sets because then you have you end up with some paradoxes. And for the same reason, you can't have a category of all categories, at least not in most formal systems, most foundations. Instead, you can have a large category of small categories, for instance. So a small category would be one whose objects and morphisms are sets. Rather than so it has the collection of objects of the category form a set. So it's not too big to not be a set. And so there's already these kind of implicit things, and there's some technical work about universes. In fact, they're called Grothendieck universes after Alexander Grothendieck.
That French guy?
Yeah. Talking about, okay, how do you actually kind of axiomatize this and represent this in the standard, well, almost a standard kind of Zermelo-Fraenkel axioms with choice for set theory. So it turns out in order to kind of do this as many times as you need to add another axiom. I don't know anything how that works, but from that perspective, category theory isn't precisely a foundations for mathematics.
That's exactly what I was wanting to get to, and so I guess to back up a little bit, I'll just give my understanding of the set theory and how it does act as a foundation currently. So we mentioned how you can't have a set of all sets and the paradoxes behind that. So there were people around the turn of the century who were trying to work out a way to ground mathematics in set theory, but they came up with certain problems. So Gottlob Frege was a logician who was working on this, and Bertrand Russell pointed out that there was a problem that you can't have a set of all sets because you have to incorporate any possible set, in which one of these would be the set of all sets, or the set of all things that don't include themselves. And so if you have everything that doesn't include itself, well, where does that set go? Because if it doesn't include itself, I'm gonna totally butcher this,
but you can see that it's like
right. It's gonna be a problem. Yeah. The Barber of Seville example is one that gives like a concrete demonstration of this. Like, so the Barber of Seville shaves everyone who doesn't shave themselves, but then does he shave himself? And so well, yeah, of course he does, but no, he can't. So anyway, so it runs into a paradox, and if you have a paradox or a contradiction, then it totally explodes your system, because you can basically prove anything. So the way that's been gotten around is that you come up with some axioms, which in a way seem kind of arbitrary, but you have to have them to be able to have a system where basically you just say, okay, well, we're not going to allow that. And that's worked. It's given a foundation to mathematics, or at least one possible foundation to mathematics. But you have to establish those conditions, and so then there are axioms. Zermelo-Fraenkel axioms, for example, basically laid all that out, the rules to make the whole thing function. So anyway, that's my understanding of the set theory, and then what I'm hearing from you is that hasn't really been all worked out for category theory.
Yeah, so there have been a couple of attempts or kind of approaches to this, and so it's not that you can't try and do foundational things in a category theoretic language, just that people don't often bother to.
Okay.
I think in the 70s there was this. I think it was Levere, who's a category theorist, came up with what he called the elementary theory of the category of sets, which starts kind of from the same sorts of basis as the ZFC axioms, the set theory axioms.
Mm-hmm.
So he's just kind of constructing a formal system that describes not kind of sets and set membership and constructing sets from other sets, but the properties of the category of sets and functions between sets.
Okay.
So the objects of this category would be interpreted as sets, and the morphisms of this category would be interpreted as functions between sets.
Okay.
And I think there were a couple of problems with that didn't make it as useful as you might want it to be, but that was one attempt. Another is type theory, which is again a different formal system meant to describe things like sets, but it's not quite the same thing. But as I understand it, you can use that much more readily as a foundation for mathematics, and a lot of things that mathematicians want to do are more easily expressed in this language.
Okay.
Than
Is trying to establish foundations for mathematics really, I guess, an activity right now? I mean, I get the impression around the beginning of the 20th century that was like a big deal, called Hilbert's project from David Hilbert. That was like a holy grail that people are after. Is that just not as much of an interest nowadays?
Yeah, most mathematicians are not really interested in foundations.
Mm-hmm.
They'll say, well, based on what I know, this can probably be axiomatized in ZFC, and so therefore it's good.
Okay.
But even if ZFC were proved tomorrow to be inconsistent, they wouldn't really care.
Yeah. So one question that I think is kind of interesting. Okay, so foundations isn't like the main thrust of what people are interested in, but one of the questions I wrote down for our outline is the motivation for these types of abstractions, or for putting together categories and basically getting into all this discipline. What is the motivation behind it? Why you would want to look at things in this way?
Yeah. And so originally the motivation came from kind of purely mathematical problems. Maybe the first thing that people kind of wanted category theory for. So in fact, category theory was invented. Categories and functors were invented so that you could define natural transformations. So there were examples of things that the mathematicians had come up with in the 40s that you could describe from a categorical perspective. If you kind of forgot all the details, you'd realize, oh, this has the structure of a functor. Mm-hmm. And in fact, they had created a whole bunch of these. These were called homology theories. So they would take, say, a topological space, so maybe a surface or like some manifold or whatever. So they would take some topological space and turn it into, and from it produce maybe a vector space or an abelian group or something like that, that kind of algebraically represents some properties of that space. Mm-hmm. And further, they noticed that if you had maybe a function between these topological spaces, some mapping of one space onto another, that would give you a mapping of the homology of one onto the other. So this would define a functor. And It turns out that they had lots of different ways of constructing things that acted like this, these homology theories. And they really wanted to know, are these all telling us the same thing?
Okay, yeah.
And in order to do that, Eilenberg and MacLean, that was it? Yeah. They came up with this notion of category and functor and natural transformation, and in particular, natural isomorphism. So it's not just that, I get the same thing if I apply, if I do this way of calculating a homology theory or this way of calculating a homology theory, it's in fact that from the categorical perspective, they behave the same. So they even do the same thing when I do, when I map one space onto another.
Mm-hmm.
So this notion of natural isomorphism was what they invented categories for. And they didn't really expect it to do much beyond that. They figured, this will be a cool paper. It proves a thing that we were trying to do. It's interesting. And then it just kind of exploded after that in the couple decades that followed. Turned out that there was a lot of structure that was very useful and interesting in a category.
Okay. Backing up a little bit on that, I just wanted to, I know our whole point of talking about this is kind of the abstraction, but I just wanted to tie a few things in if I can of like what type of objects could be brought into something like this. So you mentioned abelian groups, which abelian groups would be like commutative groups, right?
Yeah.
Okay. Is there a reason to call them abelian rather than commutative?
Not really. It's just the tradition.
Okay, that's kind of what I figured.
There are people who think we should just call them commutative groups because
right, and so commutative basically being that the order in which you apply things doesn't matter. You can switch things around, kind of like in multiplication. 3 times 4 is the same as 4 times 3. So there's the abelian group or a vector space. So vector space is a type of structure in linear algebra where you can perform certain operations of vectors, adding vectors, multiplying vectors, scaling them. So would those be objects in this framework? Okay.
Yeah. So you would have a category of topological spaces or a category of manifolds, and then you would have a category of abelian groups or vector spaces. And so homology is a functor from one to the other.
Okay. So right. So yeah, this is good because manifolds over here, and then you got your vector spaces over here. They're different things, but what are the similarities between them in their structure? That's kind of what we're looking at with this. Okay.
So you might say that this is like a functor. So people will typically write categories like this, and then it would go from this to maybe. And H would be the homology functor.
Okay. So is that a topological space there on the left?
Yeah. So the category of topological spaces to the category of abelian groups.
So
gotcha, you would have, say I have some space X, maybe I'll call it like that. And then maybe it's like this. Right. And then that's going to turn into H of X, which is going to be some, algebraic thing. So it's going to have some elements that I can add and subtract to each other, and that will have some algebraic structure. And then if I have kind of a way of mapping this down, maybe I map this down onto just like a disk. And this points all go down like this. So I'll call this one Y. And this might just be a function. Then I also have H of Y here, and also H of F. So there's an induced kind of mapping from H of X to H of Y that comes from the topological mapping from X to Y.
Okay. Excellent. So the theory kind of developed as people were doing this, and McLean and the other name you mentioned came up with a way of formalizing this to think about it as a general procedure or theory.
Yeah. And maybe the interesting thing that tends to happen with category theory is that forgetting some details makes it easier to prove things. So if you forget, how exactly do I compute this? Like what do I do to go from X to H of X, and just use the fact that it's a functor? There are some things that are easier to know because I've forgotten all the extraneous information.
Right.
And that's actually a surprisingly useful heuristic. Is all right, if I can represent something with some categorical structure, oftentimes if I know certain categorical things about what this thing does, then I can forget everything about what that that is concretely, and just prove things about the categorical structure. And that can be easier, or focus your attention on the essential details rather than distract you with the things that ultimately don't matter.
Yeah, getting back to how I was talking about how sometimes you just got to jump in and just say, okay, this is a thing, this term here that I don't quite understand, but can have a jumping in point. Even so, don't have to go back to first principles every time. That's actually very applicable to the whole discussion that we're having here. So that's perfect. Awesome. Now, you've mentioned before the Yoneta Lemma. Can you? How does that relate to all this? Can you explain a little bit what that is?
Yeah. So this is another sense in which maybe the morphisms are the important part of a category. And maybe I want to start with like an analogy. And so one of the kind of philosophical perspectives of category theory, philosophical in the sense of when mathematicians get together and talk about, okay, how should I really think about these things? Not anything that's maybe necessarily kind of what philosophers would consider philosophy, is that in category theory, you really want to understand an object by the way that morphisms into or out of it work, rather than any sort of intrinsic properties. I mean, in one sense, this is all that a category lets you do, because objects don't have any structure in a category. But in fact, category theorists will sometimes call things, you can try and do things in a category that don't fit with the kind of ethos of category theory, and they will call those things evil.
Okay.
The idea being that it's not something that you want to have to do because it's not really the right way to think about things categorically.
Okay.
So the Yoneta Lemma is the opposite of evil. It's very, I guess, good. So we talked about functor categories a little bit. And the kind of Yoneta Lemma says that, one way to think of this is that you can kind of faithfully embed any category into a functor category. Okay, what does that mean? So one way to think of this is if I have some object in a category, right? I can do one thing, a couple things. I could ask you, okay, what is the object X? And you could just point it out to me. Or I could ask, what are all of the morphisms from some other object? Maybe I have A. Like, what are all the different morphisms that I could take from A into X?
Okay.
And then I could ask, okay, maybe I have some other object B. Could also ask you, what are all the morphisms from B into X? And maybe I have another object C, and there's also morphisms from C into X. But also, I might know that there are morphisms from C into A and to B. And so I want to know maybe, okay, what happens when I compose some of these morphisms from C to A to X and C to B to X? Which morphisms from C to X do I get? So it turns out that this kind of structure is it's a functor, and it's a functor from, I'll call it, it's a functor from the category C. So maybe this is our category C, and we get a functor from C to the category of sets. So that's called set.
Okay.
And the way that this works is that maybe it says that I'll call this Y, like curly Y.
That whole structure there.
Yeah, so this functor is called Y.
Okay.
And so Y of A, so if I have some object A, this is going to be like the set of morphisms from A to X.
Mm-hmm.
So maybe I should call this like y sub x, because it depends on my object x.
Mm-hmm.
Right, and then there's also y sub. So I could, also have y of x of b, which is the same thing. But if I have a morphism from A to B, that lets me take a morphism from B to X and turn it into a morphism from A to X, mm-hmm. right? So, because I could take the morphism from B to X and then kind of pre-compose it with the morphism from A to B, and that gives me a morphism from A to X. Mm-hmm. And so this is what you might call a contravariant functor. It turns around the direction.
Okay.
Right? If I have a morphism from A to B, I get a morphism from B to A in this between these two objects, these two sets. So this would be like y of f. So the idea here is, okay, so these functors you call, like the functor y sub x is the representing functor for the object x. And the idea, and what the Yoneta lemma says, is that morphisms from maybe x to some other object y correspond to natural transformations between y sub x and y sub y. Okay. So essentially, it says that you can represent each object in a category by all of the different ways to map into it, mm-hmm. From another object in the category.
Okay.
So maybe a perspective on this. Let's say you have some 3D object, some figurine or whatever, and well, you can't see in 3D. You can only see in 2 dimensions. Mm-hmm. And you can look at, okay, what do I look at this, like what do I see when I look at this object from this angle? And then I can like turn and see, okay, what does this look like from another angle, and so forth.
Right.
And if you look at enough angles, you know exactly what the 3D structure of that object is.
Yes.
Even though you can't observe that directly. So this is one of the kind of principles of thinking about morphisms in categories sometimes, is that you can think of a morphism from A to X as being like a perspective on X.
Right.
Or maybe a way of looking at X from one perspective, maybe one set of coordinates for X.
Yeah. Right, and this is kind of this relates to the context in which you brought it up, because it makes me think a little bit of the principle of invariance, like basically that if you're looking at, we'll just use an example in nature. Like if you're looking at an object in nature, you can look at it from different frames of reference, right? So. Or units of measure. But the idea being that the principle, like say it's a property of length or something, there's going to be an invariant under all of that, and you can you can translate between the different ways of representing it. You can translate between different units, or you can, if you look at an object from one angle versus another angle, you can account for those shifts in frames of reference and determine that, okay, whatever property you're looking at is invariant under all those changes. I guess one of the questions I have is, does that demonstrate that there is a single underlying thing, or is it better just to look at all of those different perspectives and say, okay, well, all these perspectives converge in this way, versus saying, okay, it's that one thing underneath that's causing that to. That was the conversation that came up, right?
Yeah.
Because I was talking about some philosophy of science from Sunny Ao Yang, who was talking about this, where basically you have these different methods of representation, and since they are intertranslatable, that posits some kind of underlying object. And you brought up the Yoneta Lemma as a kind of another way of looking at it.
Yeah, and maybe the categorical answer to that question is it depends on what category you're working in.
Mm-hmm.
So there are definitely kind of functors from any category to the category of sets, or most categories to the category of set, that are not what you would call representable. So these, you could think of these as maybe possessing all of the properties of these sets of kind of maps for your object, but there's no object underneath.
Okay. Yeah.
In the sense that, I mean, and sometimes this happens for kind of silly reasons. You can think of it as, like I've got multiple copies of this object, or something like that.
Yeah, and I understand what you're saying, even though I can't represent it in my mind, obviously, because since it's not representable. But I get the idea.
Yeah, and in some situations, like you can think of some of these non-representable functors as being ways of gluing together objects in your original category, or of combining them that you wouldn't necessarily have been able to do before. So you can think maybe of manifolds abstractly as one example of this. So you think of it as a manifold as something that you could get by kind of patching together things that look like Euclidean space locally. Mm-hmm. You kind of glue them together. And you can think of that as in some sense being a completion of some category of Euclidean spaces.
Ah, okay.
One way to construct this that actually gives you way more than just manifolds is to actually see them as particular sorts of functors from the category of Euclidean spaces or something like that to the category of sets. And where you think of this as all of the possible maybe local charts for your space. Mm-hmm. And so in some sense, the category theorists might say, it doesn't matter whether there's actually an underlying thing. All that I can do, like I can do everything to this thing, this space or object that I could do if there really was an underlying object.
Okay.
Like all I know how to do is get these particular perspectives on this thing.
Right.
And well, I can do that just as well to this possibly fictional object as I could to something that actually was there. Mm-hmm. In that sense. So maybe phenomenologically, there's no difference.
Yeah, that's a very interesting point. Yeah, and so I mean, I guess it it definitely in the philosophy of science, I would say it undercuts a kind of conclusive nature of trying to demonstrate, like, okay, there really is a there. Not that it may not be compelling, but it can't be conclusive. And in certain instances, I get the idea that a lot of things that we could be dealing with in mathematics aren't really the type of things that are, I guess, objects in the real world, in a sense. We're just kind of looking at possibilities in a mathematical space, in a sense. But
so maybe I think we talked a little bit about quantum field theory and those sorts of, like, quantum systems. Do they have properties? And I guess one way of approaching this is as looking at a quantum system as really something that gives you some very particular set of perspectives that you can look at it at, but it's a limited set because there are sets of measurements that you can't take simultaneously, for instance.
Right.
And the question of whether, is there a definite state to this underlying quantum system or not, that might, you may be able to construct some system or some mathematical structure for which, all of these possible observations are in fact just maps into this structure. Mm-hmm. Or you could take it as just, well, all I know is that I can take all of these pictures and they're consistent in these particular ways.
Right.
And those are, in some sense, maybe from the observations that we know how to make, equivalent structures.
Yep, exactly. Yeah. They're both consistent with the data. And that pops up a lot in physics, that we have competing theories that equally describe the existing data, and without further experiments, or sometimes we just haven't figured out what experiments we could possibly run to be able to distinguish between them. Even though, and in most cases, that's just fine for engineering, developing products, and using the physics for that. We don't necessarily need to know the deeper level principles behind it. But there's also the human drive to want to understand things. Immanuel Kant, he talked about how we're always wanting to understand things beyond what we have the capacity to understand. It's kind of this tragic element of the human mind. Cool. Awesome. Anything more to say on that point?
I don't think that. Yeah, I don't think I have anything more to go through there.
Okay.
I'm looking at this diagram, and maybe that's not the clearest thing that you might hope for.
That's all right.
I hope at least this idea of the Yoneta Lemma as saying I can describe an object in terms of all the possible different perspectives on that object, rather than by inherent properties of the object.
Yeah. Well, and I really like the way you put it, that in certain conditions, it makes sense to, we can kind of construct from all the 2D perspectives an underlying 3D object that we can represent in our minds. And in other cases, there's not really anything that you could construct as in a form of representation. So you take all the different perspectives together and say, okay, that's how I'm going to think of it. That makes a lot of sense to me. All right. One other thing I wanted to get into, and I don't know if this will go very far, but in philosophy, so there's a philosophy of mathematics called structuralism, which is kind of this perspective that rather than looking at objects, we're looking at structures. But then there's also a more general philosophical approach called structuralism, which is kind of a lot of it goes back to a philosophy of language, and then also gets into epistemology. And it seems like there are some kind of parallels, though they may be loose. But I'll just kind of riff on those for a little bit. So in Ferdinando Saussure was one who came up with this idea that you have in language, you have signs, and so a sign could just be like something that we vocalize, right? Some sound that we make with our mouths. It's the primary form of sign, then also symbols that we actually write down, letters and words. How should we think about this? How do the signs relate to what they signify? And so structuralism was this idea that rather than the map from sign to signified, we should pay attention to the way that the signs relate to each other. So if you think of just the sound that I make with my mouth when I say ball, rather than it being a map from that sound to an actual ball, what we should pay attention to is the way that is situated in the other terms, right? So ball has these associations with games, bouncing, basket, throw, toss, catch. So we have all these ideas that relate, and that any sign is related to myriad other signs, and that's kind of what is conveyed in either in our minds or in a language. And then post-structuralism kind of takes that even up a level where it's not even at the level of our mind, but it's at the level of society. So a lot of that could transcend anything that we think about. And then that's sort of related to kind of coherence theories of truth and epistemology, where rather than trying to find foundations, I think this sort of relates to category theory as well, but rather than trying to establish some definite axioms to know, like, that there is an external reality out there and that this is how we can ground making definite truth statements, we just look at, okay, how do statements that we make relate to each other? And so I can hold this statement in my mind and I can hold this statement in my mind, and the two cohere with each other. So that's coherence versus correspondence, right? So that I can hold all these things together in my mind, and they don't contradict. Willard Van Orman Quine talked about a web of belief where you have all these different beliefs and they all fit together, and that kind of what we do is as we learn, we make adjustments to the web. So, like, say one section of the web gets damaged, and we learn that something we believed wasn't true. Basically, that affects the way we think about the whole system, and we rebuild to put the web back together. And so it might affect knocking down one belief might affect a few others, or change, modify. Certainly some applications to religion and belief there. But anyway, so there's this whole perspective on philosophy of looking at structures, coherence between different beliefs, and I was thinking of that analogy as we were getting into category theory as well.
Yeah, I think that's a very apt analogy. There's one kind of concept we didn't really talk about, which is isomorphism, which from a category perspective is kind of the right notion of is the same as. So as you were talking about, when you think about signs and their relationship with the signified, well, rather than trying to construct the relationship between the sign and the signified, you look at the relationships between the signs themselves. So maybe one idea is, okay, well, when do two signs signify the same thing, or when are two signs the same thing? And you might think, okay, well, if I could replace this sign with this other sign in any situation, and it would fit in the same setting, the same format, those would be the same. They might not be strictly the same sign, but they would be equivalent in that sense. Maybe in a category theoretical perspective, or from a Yoneta perspective even, like if all of the morphisms from one object into another kind of correspond with the morphisms from a different object into that object in this kind of one-to-one way. That's going to make those objects isomorphic. And so from the perspective of the category, they're essentially interchangeable.
And when you were saying that, I was just thinking of how the way the whole structures can become objects. So like in quantum interpretation, you have your various interpretations of what happens when with a measurement. So like the idea of a wave function collapse, that you're going to a particular eigenstate. There's wave function collapse is one interpretation. And then multi-world or many worlds would be that it doesn't collapse, but basically you splits into different worlds in which the observer is in one of those worlds where it looks like it settles on one eigenstate, but really other eigenstates are, I'll just say outcomes, eigenstates being outcomes, are observed in other worlds. Those basically you could put in either one, and I mean, would you say that those are isomorphic in this way we're talking about?
Yeah. So typically, I think you would talk about isomorphisms in the context of maybe structures being isomorphic, or of objects in a category being isomorphic. So in a sense, that might be a level lower than typically one talks about isomorphism.
Right.
So you'd say you could say that like the set of outcomes of this experiment is isomorphic to the set of possible outcomes of this experiment.
Okay.
If there's a way of kind of matching them to each other in a way that, well, if I had this outcome from this experiment, that's basically the same thing as having this outcome from this experiment, and so forth.
Yeah, very interesting. Cool. All right, let's see. I think we basically covered all the points I was wanting to get into. Cool. Anything else you want to talk about on this? No,
I'm pretty happy with where things have gone.
So let me ask you: does this come up in your own work?
Yes and no. So categorical language, at least, is incredibly useful in a lot of fields of math. Actually doing maybe what category theorists would call category theory is not always as useful. So, for instance, one of the things that I study are called sheaves. So they're a kind of algebraic topological structure. You think of this as a way of kind of attaching or of describing how data is attached to a space, and maybe how that data should vary as you move across the space. How should it be connected? What are the consistent kind of assignments of data to the space?
Okay.
And so that is described, has a very nice, concise description in terms of category theory. In fact, a sheaf is a particular sort of functor from a category that's associated to a space to a category whose objects are kind of like data. They are things that could contain data. They could just be sets. They could be vector spaces or things like that. And so that, like, having that language to describe it very compactly, rather than, right, I can write down all of the kind of conditions that everything has to satisfy, but that's complicated, and that sometimes gives you nice perspectives on how to do things. It's definitely comes up in the things that I do, and I try to do work that takes kind of these abstract ideas and turns them into something that you could possibly use in some kind of maybe an engineering type of system. Maybe you're designing something for a collection of kind of networked robots to coordinate towards some goal, or you're trying to analyze data associated with a network or something like that.
Okay, awesome. One other question. So kind of a related topic that I've been thinking about is structure in general, just trying to think about, okay, what is structure, and getting into kind of the philosophy of that. So, I mean, even just like in all applications, right? So like, so there are mathematical structures, there are physical structures that you can build, there are chemical structures, conceptual structures, even spiritual, religious, narrative structures. But I don't know. Do you have any thought on that, or a definition that you have working with that would describe, okay, what is a structure in general?
I don't know. Maybe I'll throw out something that's probably inaccurate, but
that's all right.
It's kind of a mathematician's way of thinking things, is that a structure is whatever is invariant under isomorphism.
Okay. Interesting.
It's not really an answer, because then you have to say, all right, what makes something an isomorphism?
Right.
Right. But it's if you have a notion of isomorphism, then you kind of have a notion of structure, because it's just kind of what doesn't change when I go through an isomorphism, mm-hmm. when I look at something that's isomorphic to what I had before.
Yeah.
So maybe that's the mathematician's answer is unhelpful, but maybe clarifies
I like
a different way of looking at it.
I like that one. Yeah. And another avenue I've been trying to think about is like in terms of, I guess, complexity or relations, or even entropy. Right, I kind of relate into information theory, but I don't know if that's the right way to look at it or not. But like, I guess I want to say like, but that's kind of more in quantifying structure. Like, how does the amount of structure?
Like how much structure is there? Yeah.
Yeah. So like, say you have a set of organic atoms. So like you got your carbon, nitrogen, oxygen, phosphorus, and then put it together in amino acids, and then put that together in DNA molecule, mm-hmm. and then what is the way to think about the way that all that puts together in the structure that's building?
Yeah. Well, so maybe here's a way to unify those two perspectives. At least in narrow settings. Mm-hmm. So like in thermodynamics, often you'll, as I understand it, you'll construct this notion of entropy in terms of kind of microstates that give you indistinguishable macro states. Mm-hmm.
Right.
So you might have, you could give a microstate by specifying the position and velocity of each atom in your gas for these, huge numbers of atoms, mm-hmm. Or molecules. But this notion of indistinguishable macrostates is kind of giving you a concept of isomorphism of microstates.
Oh, yeah.
And in some sense, and I think you can make this rigorous with some sort of category theoretic stuff. Or anyway, the idea is that maybe, the more microstates correspond to a given macrostate. So the more microstates are isomorphic to each other, the less structure there is.
Yeah,
the more entropy there is, because there's clearly not as much structure, because there's a lot of different things that are still all isomorphic.
Right. Okay. Yeah. Very interesting. Cool. Well, I'll have to keep bouncing those ideas off you in our forum, and then maybe we'll regroup again to go over some of that. But anyway, that's just something I find kind of interesting. But very cool. All right. Well, thank you very much for coming on and working through these things with me. I like the interplay between professional mathematician and amateur math enthusiast. Hopefully, that's somewhat interesting and productive for anyone who happens to be listening, but at least is for me. So,
I've enjoyed it. Thank you.
Yeah. All right. I'll talk to you later.